We found that when you turn a circuit on, if there's any inductance in that circuit, then the current doesn't just immediately jump up to its final value. It takes some time for the current to build up to its final value if there is that inductance representing some electromagnetic inertia in the system. Now here, we're going to turn off our circuit. And while we expect our devices to turn off instantly when we push the off button, what we're going to see here is that if there's any inductance in the system, then there is going to be an electromagnetic inertia that will cause the system to sort of persist, our current to persist for a while, even after we turn the circuit off. It's going to take time for that current to go from its present value down to zero. It takes some time to ramp down. So here we're going to try and solve for the current as a function of time after we turn a circuit off. Okay, so here suppose this current has been running around this loop for a very long time, so it's reached some stable final value. Our inductor is just behaving like a wire at the moment, and our current is steady and constant around that loop. Then we throw this switch to remove the battery from the circuit that ought to turn the circuit off. The current should disappear. But what we're going to see now is that it takes some time for that current to disappear. Throwing that switch over here, our current is then going to run around this loop for a little bit. So okay, we're going to throw that switch there at time 0. And let's write our Kirchhoff-Faraday loop equation here. I'm going to imagine a path that goes in the direction of the current at present. So the current has been going down through this branch. Let's make down the positive direction for the current. And so our Kirchhoff loop, or our Faraday loop, is going to go like that, counterclockwise around that path. So our equation will be 0, as in the total sum of all the voltage, of all the potential differences, equals, and then moving along that path, we've seen that if we move through an inductor in the direction of positive current, then that contributes a minus L di dt term. So that's the EMF across our inductor, our back EMF, our self-induced EMF in this coil here. Then continuing to move with the current through the resistor, that's minus IR, and that gets us back around to where we started. And there we go. Those are our only two terms in this loop. Note that these two minus signs, which may seem confusing, they come to us because we're going with the direction of positive current as we've defined it. With the current through an inductor, minus L di dt. With positive current through a resistor, minus IR. Okay, so throwing the switch at time 0, the current that had been running through this branch before we threw the switch will be the current running through that branch immediately after we throw that switch. This current through an inductor cannot change instantly. It takes some time. So at time 0, if we throw that switch, there's going to be a non-zero initial current through this branch here, which means since that current only has one place to go, there is an initial non-zero current running through this whole loop. It's equal to whatever the current was in this inductor before we threw the switch. Okay, so let's call that I0, the initial current. And we see from our equation here that if I is equal to I0, then we have an initial rate of change of the current as well. Our EMF through our inductor must be equal to I0R, as I state here, and our initial time derivative of that current must be equal to I0R over L. So those are our initial conditions. And we see here that at that initial moment, our EMF is going to be positive, so pointing in the direction of positive current, and our inductor at that moment is behaving like a battery, trying to keep the current going. The current was going down in this direction. By removing our battery from the circuit, the current is going to start to die out. Current is going to start to dissipate. Our inductor here, with its inertia-like effect, is going to try to keep the current going. So it's going to behave initially like a battery, pushing the current in the direction it had been going. All right, so this is what our loop looks like at time 0. And so there's our initial current, or rather our initial EMF here in the inductor. We see that that will actually be equal to the EMF that the battery was providing. So at the moment we flip that switch, our inductor, at least for an instant, behaves exactly like the battery that had been driving the current. It sort of takes up the role of the battery for a moment to keep that current going. But alas, our inductor cannot keep that up for long, because if the current is changing, then our EMF is changing. Already here. And we see that our current is initially changing. Here's our initial rate of change of the current. So that's going to lead to a diminishing EMF in our inductor over time. If we wait a really long time, time goes to infinity, our current must approach some final constant value. So if I is approaching some constant, then di dt is approaching 0. So if we wait a really long time, then di dt approaches 0, so the EMF through our inductor approaches 0. So if this approaches 0, if that EMF through our inductor approaches 0, then we see that I must be approaching 0 as well. So we've concluded that, yes, as we expect, the current will eventually go to 0 here, but it's going to take time. Okay, steps for solving that differential equation are Kirchhoff-Faraday loop equation here for the current as a function of time. Following the method I presented in the last video, first we're going to get the di dt by itself on one side of the equation. Then I want to factor out any coefficients off of the I to get the I kind of by itself, and we actually don't need to do any of that here. There's only one term on the right-hand side. So next, just get all the i's together on the left and the t's together on the right. That is, we multiplied both sides by dt here to move the dt up. So we've got the di over I and the dt times this. And at this point, we notice that we've got current over current, so that's dimensionless. Therefore, this side must be dimensionless. So if this is a time, then L over R must be a time as well. And we define our RL circuit time constant, L over R. It's called the RL time constant, even though it's not R times L, it's L divided by R. Okay, now we're ready to integrate, set our initial conditions. At time 0, this is key, we have a non-zero initial current this time. So at time 0, our current is that initial value, I naught, and we're going to some future time t, at which our current will be some future value, I of t. Okay, find your antiderivative and simplify, and we get exponential decay for our current in this circuit. Starts at some initial value, I naught, and decays away. The time constant tau, that's the time it takes to decay down to about 2/3, 1/3, down to about 1/3 of its initial value. So that time constant characterizes roughly the time scale on which it takes that current to die away. It drops to 1/3 of its initial value in time tau. So you flip that switch, turn that circuit off, it doesn't go off instantly. This zombie current sort of persists for a little bit, decays away exponentially, doesn't instantaneously disappear. That's the role of our inductor, that electromagnetic inertia in the system, causing this current to persist even after we've removed the battery from the circuit. One last step here, we could also find the EMF across our inductor here, minus L di dt. So take that derivative of this equation, multiply by minus L, and we get this, and see that the EMF across our inductor is also going to be exponentially decaying with time.